not being to make you run out of time. So there's an example of a DC analysis. I just assume that things are forward biased. Now, if you see something that's obviously wrong, like here, let's say that this diode was facing the other way. What I would do is I would say, okay, yes, this one's going to be forward biased because we have a positive voltage and ground, so current's going to want to go through this way. Current's going to want to go through this way. That diode's reverse biased. That doesn't make sense. There's going to be no current going through here, right? So I'm going to assume that that's off. That just looks like an open circuit. So if I see a diode that appears to be pointing in the wrong direction, so if it appears to be reverse biased, I just take it out of the circuit. Okay, then all the current would have to go through that branch there. That would change your numbers. Okay, so that's DC analysis. Let's do an example of small signal analysis. All I want to say about small signal analysis for a diode, because it's the same for BJT. Small signal analysis of a diode is like this, right? You replace your diode. You got your small signal coming in here, right? So that's supposed to look like a sinusoid, only I just can't draw sinusoids very well. So you have your small signal coming in here. And what does it see? It doesn't see a diode, it sees something that looks like a resistor. We call that R sub D, which is equal to VT, so the thermal voltage divided by that bias current. So the bias current allows us to set what that equivalent resistance looks like. So if I want a high resistance, I pick a low bias current. If I want a low resistance, I pick a high bias current. So depending on how I want to use that equivalent resistor, I can set it depending on my bias point. So that's why I choose the bias point to be a particular value, to get an equivalent resistance that will do something, whatever that diode is supposed to do with it. That's all I want to say about that, because it relates to the BJT stuff directly, so I'd rather spend time talking about that. Okay, the BJT question, I do want to do the one from the previous finals, because again, this is just like what we did in class. The fact that this is just like what we did in class, it's just like what you did on the previous final, maybe gives you an indication that this is an important circuit. Also, it was worth 1/3 of the marks last time, so you might want to make sure that you understand it. Or maybe that's something you had to say. Make sure that you attempt to understand it. So do your best to study this stuff. It's all understand. Okay, so here's how it was drawn. Okay, so if you recall what we said in class, there's two parts to this question. Before I even ask any questions that were stated here, you know exactly what you're going to need to do. You're going to need to find the DC bias point. So what I mean by bias point is you're going to have to find the currents and the voltages at the nodes. Right? So here's your DC part of the circuit. It always just comes down to, for this configuration, for this common emitter configuration, it always comes down to these four resistors and BJT. Actually, for all the single transistor stages, it usually comes down to four resistors and the transistor. So part one is going to be find the DC operating point. So here's the DC part of the circuit. And then, as you recall, for the small signal part, we can short out these capacitors. So for the DC part, capacitors look like opened, so we only have this in the box. For the small signal part, the capacitors look like short. So the capacitor goes away and we just replace it with a short. And we'll draw the small signal model in a minute. But first we need to find the DC point. And not surprisingly, the question actually begins with that. So, sorry? Oh, that's okay. Sorry, I just thought of it. So we're gonna look for VB, VC, VE, IB, IC, and IE. And then we're given all of these values here. So let me just write them on here. I think it's maybe the easiest way to do it. So VCC is 12 volts. 12 volts. RB1 is 91K. RB2 is 18K. I'm sure those numbers work out nice, hopefully. RC is 5.6K. Okay, RE is 1.2K. And RL is 8.2K. RI is 50 ohms. So that would be like your 50 ohm cable that connects things up. Do we care about any of the other? So they actually give capacitor values. Just ignore that if you see this on the test. If you see this anywhere, actually, for the kinds of circuits you're dealing with in undergrad anyway. Small signal capacitors. So capacitors that are in circuits where you have to do a small signal analysis, you generally just assume that they are short. In fourth year courses, you will actually put in the impedance of 1 over S omega, or 1 over SC, but you don't do that until fourth year. You're also going to be told here that beta equals 100.
Don't forget.
Interestingly, we just explicitly tell you that VBE equals 0.7 volts, and also VT equals 25 millivolts. Okay? So notice that we drew it a little bit different. I don't want you to get confused by the way we drew it. Remember before in class we drew CE directly in parallel with RE, and that shorts out RE at the small signal. We did the same thing here. I just drew CE pointing to the right instead of pointing down. There's still ground on the other side. There's nothing topologically different about this circuit. It's just drawn slightly different. I don't want you to get mixed up because of that. Oh, I need to annotate one other thing. Okay, so the question says, supply the DC circuit model of the circuit in the dash box along with the DC voltage. You don't really need to redraw it, it's already there. So here's what we can say. Remember that the first thing we do is we look at the source. We replace the RB1 and RB2 in VCC with its Thevenin equivalent. So what you end up with here is 12 volts through 91K through 18K. What this looks like from a Thevenin point of view, if I'm looking over here, this here is equivalent to that in parallel with that. Well, okay, so my open circuit voltage, let's figure that one out first. That's going to be VB is what we'll call it, is equal to 18 over 91 plus 18 times 12 equals 1.98 volts. I guess it did work out nicely, by the way. And then my RBB, which is the Thevenin equivalent resistance, RBB equals 15.0K. Maybe I should just tell you where that came from here. It's RB1 in parallel with RB2. So the whole DC part looks like this.